135 world-class laboratory and engineering facilities, and 30 major active test stands capable of handling nearly any challenge.
Report B-cell pressure to TC. Start Pacific high-speed recording.
Copy, high-speed recordings.
65 square miles of the Mojave Desert. Plenty of room to test advanced rocket propulsion technologies. There isn't a better place to do rocket science. The facilities at the Air Force Research Laboratory's Rocket Lab are highly flexible and adaptive. They are used to characterize, test, and validate the ever-changing advancements in rocket propulsion technology for the Air Force and DoD. No place else in the country boasts the capability of doing basic, exploratory, and advanced research covering the full gamut of spacecraft, solid rocket, and liquid rocket propulsion. While being environmentally compliant and friendly, our operations are continually evaluated to ensure they do not adversely impact the local endangered species.
3, 2, 1.
Because of this and lack of encroachment issues, numerous external customers use our facilities, including NASA, Air Force Global Strike Command, and many companies as part of their efforts to develop and qualify new systems for their government and commercial customers. We not only conduct in-house and contracted research efforts, but also execute mutually beneficial research efforts with companies through cooperative research and development agreements. These CRADAs and commercial test agreements allow for companies to use our facilities in support of their commercial developments. We currently have 3 commercial test agreements resulting in long-term leases of facilities at the Edwards site. Our solid rocket capabilities cover the full spectrum from gram quantity liquid and solid propellant development in our chemistry laboratory to full-scale liquid and solid propellant mixes at Area 130. We are exploring continuous flow reactor chemistry to quickly and efficiently scale up and produce new propellant ingredients. This small reactor can produce pounds of material in a few hours and can be coupled to create full-scale manufacturing capability at a fraction of the cost used for traditional manufacturing technologies. Area 130 is used to scale up ingredients and characterize propellants for mechanical properties, chemical performance, and hazards. We produce up to 500 gallons of the non-toxic monopropellant AF M315E, the next generation of storable in-space propellants. We can also scale up solid rocket propellants from pint to 1, 2, 5, and even 50-gallon mixes, which can also be used to conduct validation and verification of contractor propellant formulations. Our rocket-focused composites facility allows us to design and fabricate components using advanced materials and design techniques for testing in relevant environments. With our 6,000 cubic foot clean room, 4-axis winding machine, curing oven, and autoclave, we can fabricate large tactical-sized motors up to 24 inches in diameter and 8 feet long. With our propellant scale-up and composites facility, we are able to conduct subscale as well as full-scale component development and testing of new technologies. Area 132 is capable of handling subscale motor tests ranging from 2 to 70-pound motors, and full-scale motor test up to 1 million pounds thrust without thrust measurement, or up to 250,000 pounds with full 6-component thrust measurement. Pad 1 and 2 were modified and expanded in 2004 to handle larger motors such as the first stage ICBM motors and Atlas V strap-on booster. Even larger motors can be tested on a number of other stands, including Stand 1C, which was most recently modified to test the 1.6 million pound thrust Titan IV solid rocket motor upgrade. The stand has a full 6-component thrust stand and the enclosure enabling testing at temperatures from 40 to 90 degrees Fahrenheit. Our liquid engine test stands were originally built for the Atlas ICBM and Saturn V F1 engine development programs. They have received massive upgrades to include a state-of-the-art data acquisition system with over 1,200 data channels, and today are a key component to our technology development efforts. Stand 2A is a high-pressure facility with 10,000 psi lines to handle the most complex liquid engine testing possible. It is used for both component development and full-scale engine testing, and is currently conducting component and full engine testing under our hydrocarbon boost demo program. The stand was recently used under our upper stage engine technology effort to validate physics-based modeling, simulation, and analysis tools for liquid rocket engines. Test stands 1A and 1D are full-scale engine test stands. They are used for technology and system development testing and are capable of handling engines up to 2 million pounds thrust. Stand 1A was most recently used under a commercial test agreement for the development of LOX's hydrogen RS-68 engine used on the Delta IV. Our liquid engine analysis and component evaluation capabilities are critical to understanding the underlying physics and phenomenon occurring in the chamber, injector, and other components. We can characterize fuel properties and cooling schemes using our highly modular single-element EC1 and high-heat flux EC3 rigs. We developed the specification for RP2 and characterized it for use in both expendable and highly reusable launch vehicle engines. We have a high-pressure cold flow facility at Area 114 used to understand injector flows at subcritical pressures. We use our unique supercritical EC4 facility to understand injector performance when subjected to outside disturbances. We can do this in both cold flow and hot fire conditions, the results of which allowed us to validate a previously unknown ignition method. These facilities have been instrumental in helping industry partners resolve issues with their proprietary chamber and injector designs. Our high-temperature components group conducts research on rapid densification of carbon-carbon and micro-manufacturing for rocket components. The rapid densification carbon-carbon technology has been commercialized by Allcomp Incorporated through Accreta and produce over 6,000 parts per month for both commercial and military applications. Rocket propulsion can be a hazardous business. We have the capability to fully characterize the hazards associated with the technologies we develop and support outside customers with analysis of their systems. Our analytical chemistry laboratory has all the tools necessary to assess propellant, fuel, and fluid purity, identify unknown components, and support our chemists in the synthesis of new compounds. We characterize the hazards for new propellant ingredients and formulations, as well as conduct numerous system-level tests. Altitude facilities are a critical part of our technology development capabilities. Our electric propulsion facility boasts 7 chambers capable of simulating space vacuum and conditions. We can measure thrust down to 10 to the -8 newtons. Our largest is our 10-foot by 32-foot long-duration chamber, which has been used for life testing of Hall effect thrusters up to 4.5 kilowatts of power. The 30-foot diameter SPEF chamber at Area 142 uses diffusion pumps and is capable of handling greater than 10 kilowatt high-power electric propulsion and multi-mode thrusters. We recently modified eCell at Area 142 to handle chemical thrusters for spacecraft and boast an extensive diagnostic capability enabling true comparisons between different vendors' thrusters. The facility can test chemical spacecraft thrusters to full duration or small solid rocket motors up to 200 pounds thrust. Area 142 has undergone significant upgrades over the last 15 years and is the site for our large altitude thrust chambers capable of simulating 100,000-foot altitude and handling either liquid rocket engines or solid rocket motors up to 50,000 pounds thrust. All three strings were recently used to test technologies for an advanced third stage for ICBMs using ACell. The Navy Standard Missile Office has been conducting ongoing third-stage rocket motor development and production verification testing in B-Cell since 1997. Smaller upper-stage thrusters are handled at Area 114. Cells A, D, and E can simulate 100,000-foot altitude, while Cell C can simulate space and is used for spacecraft chemical thruster development and testing. Cell B is a sea-level stand handling thrusters up to 15,000 pounds thrust. The facility is capable of handling LOX hydrogen, hydrocarbon, and toxic bipropellant combinations. Aerojet Rocketdyne has a multi-year commercial test agreement to use D and E cells to support the THAAD missile defense system. "65 square miles of the Mojave Desert. Extensive, world-class resources and facilities at your disposal.
Start sequence.
There isn't a
Sequence
better
start.
place to do rocket propulsion, research, and development."